Okay, looks like we're live. All right, so this is the review week, the fourth week of my series of videos about probability. I'm here, I am Doug. I am happy to be here, and my beautiful assistant Mocha is also here. Yet again, as usual for probability, there's not very much for her to do, except to look pretty and try not to get in the way so that I don't step on her. Now, what's going on outside? It is hazy and cloudy, but it is still hot. I'm glad to be in the basement. We have had wildfires, and that's been now going on for several weeks, 3 weeks or so. They seemed to go away for a couple of days, and then they came back. So it's very hazy, and we get the sun looking like an orange ball during the day, which is weird. It is nice to be down here because it's also very humid. Today's shirt is Reading. Now, I know someone who lives in Reading, Pennsylvania, but this is from Reading, England. This is a team that is sometimes in the Premier League, but not always. Let's get into the math. Now, it is a review week, so there are a lot of topics, and they're all topics that I've covered before within probability. The first one I'm going to do is going to involve the whistles. So we have a bag of whistles. And for those who are not already familiar with my bag of whistles, they look like this. There are 6 of them. There are 2 red ones, 2 orange ones, 1 green one, 1 yellow one. But what I'm going to review with the bag of whistles is the idea of certain, likely, and impossible. So I have a few single event probabilities to look at using the bag of whistles. We're not actually going to pull a whistle like usual. I am using it as a prop, and we do most of our work with theoretical probability, which is calculations. So the first one I am going to put is blue. The chance of getting a blue whistle when you reach into this bag is 0 out of 6. There are 6 whistles, but none of them are blue. So that fraction is equal to 0. There is a 0% chance, and that makes sense because it's impossible. This is a review of the idea of something being impossible. It is impossible to get a blue whistle from a bag that has no blue whistles in it. The second example is getting a whistle. Well, all of them are whistles. So out of 6 whistles, 6 of them are whistles. So this fraction is equal to 1. And that is because it is certain. It is certain when you reach into the bag of whistles and pull out a whistle, the thing that you get will be a whistle. Certain. Third question. Oh, how about not yellow? Not yellow. Well, there is only 1 yellow whistle, so the total is 6 whistles. And how many of them are not yellow? There are 5 that are not yellow. So that is actually very likely. I'll write the letters at least. So I'll write IM for impossible and CE for certain. And here what we have is LI for likely. It is likely that you will get a whistle that is not yellow. It is more likely than getting a yellow whistle. A fourth example, green. How about getting green? Well, there is only 1 green whistle out of the 6. So there is a 1 in 6 probability, and that is kind of unlikely, but it's not impossible. It can happen, but we can say it's unlikely because most of the whistles are not green. And finally, I want to compare, so I'm going to write the word compare. And the 2 things I'm going to compare are going to be getting a red whistle and getting an orange whistle. So put red here and orange here. Well, there are 2 red whistles out of the 6. So we have a 2 out of 6 probability. It reduces to 1/3. It is equivalent to 33.3%. And the orange whistles, there are 2 orange whistles. It's the same. There are also 2 out of 6. The probability of getting a red whistle is equal to the probability of getting an orange whistle, so these are an example of equally likely. Put it like that, a little messy. Okay, that's sort of the basics of our probability unit. It's a very basic concept that we dealt with at the beginning, but I wanted to review it, and now we have done that. So we have looked at all of the various things that can happen, actually, for a single event probability. Now, for my next topic, I'm going to do some erasing. For my next topic, I'm going to use one of my cloth bags, but I'm going to put some different stuff in it. Stuff that I wasn't using in the previous lessons. So we are going to use pattern blocks. Which bag is it? That's the whistles. So here's the other bag. This orange bag has pattern blocks in it. Now, what are pattern blocks? We've probably all seen them before. This is a pattern block. This one is shaped like a trapezoid, and it's red. And I have 3 types in here. I also have yellow hexagons. And if I can find one of the other ones, blue rhombuses. So that's pretty good. Now, how many of each do I have? Well, I don't want to actually reveal that. I want us to at least partially calculate. So I am going, and I haven't even said yet how many of these pattern blocks are in here. What I will say is that 1/3 of them are red. And 1/4 of them are yellow. How many of them are there altogether? Well, actually, I'm going to answer that later. First, I'm going to say, let's calculate how many of them are blue. So if we know 1/3 are red and 1/4 are yellow and the rest are blue, there's only 3 colors, then if we subtract 1/4 and 1/3 from 1, it has to give us the fraction of them that are blue. So we'll do this. 1 minus 1/3 minus 1/4. Reviewing our fractions techniques, we know that we need a common denominator. And the lowest common denominator for 3 and 4 is 12, so I'm going to convert these into fractions over 12. 1/4 expands to 3 over 12, 1/3 expands to 4 over 12, and 1 is equal to 12 over 12. So if we do this subtraction, 12 minus 4 is 8, minus another 3 is 5, we have our answer. 5/12 of the pattern blocks that are in here are blue. And how many does that mean there are? Well, it depends on how many are in the bag, and I'm going to reveal right now. Oh, wow, interesting. I just looked in there and I saw this. There's still a marker left in the bag from the last time I used it. Okay, so that makes things a little bit more like I planned. There are a total of 12 pattern blocks in the bag. That is I have revealed. So we know that if there are 5/12 of 12 pattern blocks are blue, that means that there are 5 blue ones. So I'll write the 5 here. And of course, if 1/3 are red, 1/3 of 12 is 4, so there are 4 red. 1/4 of 12 is 3, so there are 3 yellow. 4 plus 3 is 7, plus 5 is 12. It works. These add up to the 12 I knew I had. It makes sense. What have we done? We have used the concept of complementary in a slightly more challenging way than some of the other questions I've done. If we subtract everything that is not blue from the bag, we subtract everything that is not blue, the fractions of everything that is not blue from 1, we get the fraction that are blue. If we know what the total is, we can calculate how many of each we have. Okay, so that was my next example. Let's move on to something else. A little problem. I don't want to write the whole thing out because it's sort of wordy, so I'm going to say it and I'll just write some notes about it on the chalkboard wall. Let's erase this. Okay, and 40% of my students ride the bus. Okay. And I'm going to choose a student's name at random. What's the probability that the student does not take the bus? We're using the concept of complementary again, except we're doing it with percentages instead of fractions. And this is not a very difficult calculation. 100% of my students minus the 40% who ride the bus means 60% do not take the bus. So that's a quick little problem, and the only reason I really am including it was because I wanted to use the concept of complementary with just straight with percentages instead of involving fractions, just to show that, yes, of course you can do that. Percentages and fractions are both extremely useful with probability. Now we're going into my next example, which I'm going to call my thumbtack example. Checking the time, we're doing pretty good. I've only used about 10 minutes. I'd like to make this lesson last just about an hour. The thumbtack example now. Is this the best example I've ever come up with? In some ways it's pretty good, in other ways it's not the best, but I wanted to use it. So what I'm talking about is this little container. And I will, of course, if I'm going to make this random, I throw the thumbtacks into a cloth bag or something so that I can't see them. But this shows what we have. We have a container of thumbtacks with 3 colors. There are some yellow ones, there are some red ones, and there are some clear ones. That sets up our question. As you can see, we're not doing very much experimental probability. When we do experimental probability, it'll be different, but when we're doing theoretical probability, we use these things as a prop, but we actually answer our questions using the chalkboard in my case, or using pencil and paper. We use theoretical probability to answer the questions. Okay, so we have, let me see. I'm just going to list what we have. So we have 8 red, I'll just leave that there for now because I won't need that much room. 8 red thumbtacks, I'll just write the word tacks. And we have 4 yellow. And how many clear? We have 12 clear. What the question is, though, is if I pull randomly and replace 120 times, I am going to erase after all. I want to make some room to write the question out. Pull randomly and replace. Things that have to be pointed out. That word randomly is very handy for me because when you see the clear container with thumbtacks in it, you can imagine that you're going to pull them, but it's not going to be random because you're going to be able to see the color of what you pulled. But if you say pull randomly, then you know that's not what we're doing. We're not going to choose a color. We're not going to pull while we can see the color. We're going to make sure it's random. And that means that we're doing something like putting it into a container that we can't see through. And then, of course, replace is also important because we don't want what we get the second time to be dependent on what we get the first time. And what we're going to do with this is we're going to try to predict. So this is a prediction. We're going to predict how many reds, I'll write number of reds, red thumbtacks, if we pull randomly and replace 120 times. I'll write that here. Make sure that it fits on the chalkboard well and it fits easily, that's good. So let's predict the number of reds. Do you want to pull a thumbtack out of any container that contains those thumbtacks 120 times? No, you don't, and neither do I. And I'll tell you 2 reasons why. One is thumbtacks are actually a horrible choice of an item that you pull from a bag without being able to see because you're going to end up sticking one of them into your fingers. Eventually it's going to happen, it's going to hurt. But the other thing that makes you not want to do that is 120 times, that's long. So what we're doing is we're using a calculation to predict how many red ones we get if we were to pull 120 times. And we're going to do that with probability, theoretical probability, and I'm not going to actually reach into any container and pull out a thumbtack even once, so I won't hurt myself. Okay, so how do we get this answer? We have 8 red tacks, and that we can call that our successful, out of a total of 24. 8 out of 24 are red. And then we can reduce this fraction. if I divide top and bottom by the greatest common factor, which is 8, 8 divided by 8 is 1, 24 divided by 8 is 3. We can see that 1/3 of the tacks are red. And then we just have to say, well, what's 1/3 of 120? That means 1/3 times 120. Oh, I'm going to have to fix this chalk. And that is giving me, if I say 120 is, if I want 120 as a fraction, I put it over a 1. I get 120 over 3. And I see that I'm going to get 40 red thumbtacks. I'm able to predict how many red thumbtacks I'll get, even with a large number like 120 pulls with replacement, simply by seeing what is the probability of getting a red in the form of successful over total. It works. So that's a cool example that didn't involve me having to poke myself with a thumbtack, and I think I'm finished with the thumbtacks for the rest of this lesson. Okay, now my next example involves the orange and green pattern blocks. So we already saw the red, blue, and yellow pattern blocks, which were also shapes. I also have some orange and green pattern blocks. Okay, what am I going to do this? I'm going to show you just one of each. I'm going to empty this bag so that I can use it again. And I'm going to just show you one of each. And we're going to talk a little bit about how useful the word randomly is again. So this is an orange pattern block, which happens to be square. And this is a green pattern block, which is a triangle. So the bag isn't only going to have one of each. We're going to imagine that we have a bag that holds 200 of them. And we don't know how many are green and how many are orange. But we're going to try to figure out how many are green and how many are orange, because we're going to give the results of a pull and replace experimental probability. So I will erase first. I'll erase this. Let's see, I should erase all of this. Okay, because it's about thumbtacks anyway. Let's get some information on the chalkboard. We have 200 in total. I'll just write 200 total. And some of them are green, and some are orange. Okay. We're going to randomly pull and replace, so I'm going to write that. Randomly pull and replace. Very useful, once again, because it tells us a couple of important things. The fact that we are replacing means that we are we're using independent probability, and what you get the second time will not depend on what you got the first time. And the word randomly helps because you saw that these are actually two different shapes. So if someone really wanted to, they could reach into the bag and they could get the orange one simply like this. Looks like magic. No, of course it's not magic. I know that the orange one is square, so I was able to feel it. But that wouldn't be random. So I'm talking about randomly pulling and replacing. Let's say you reach in and you just touch one of them. You can't tell what shape it is because you just touch it with the tip of your finger, but you make sure that you pull out that one and you don't care whether it's a triangle or a square. Then it's going to become random. So imagine a bag of 200 of them. I think I would need a bigger bag. We're randomly pulling and replacing. And how many times are we going to do this? 10 times. And let's say the results are 3 orange and 7 green. We can use this as a representation of how many orange and how many green are likely to be in the bag. So this becomes an experimental probability situation, which means that we're not always going to get exactly the correct answer. We're going to get an answer that gets pretty close to the correct answer. So the total that I pulled was 10. If 3 out of 10 were orange, then I can say that 3/10 of the 200 are orange, and I can create a little problem that looks like this. Now there's more than one way of doing this, and depending on how much experience you have with fractions, with algebra, and in this case with cross multiplication, which is part of algebra, you might find it easier or more difficult to do, depending on where the student is at and what they've learned. But using cross multiplication, bottom times top gives me 10 times x, and 3 times 200 is the top times the bottom on the other side. So I get 10x equals 600. Divide both sides by 10. These cancel. Am I running out of space at the bottom? It's actually fitting quite well. It's reaching this camera angle is nice and wide. So x is alone, and it is equal to 600 divided by 10, which is 60. Therefore, since the 3 out of 10 was the orange of the total, it means that I will have 60 orange. Oh, this is getting messy. I can still read it, but it's getting messy. And then to get the rest of the answer, well, how many are green? We can use the concept of complementary. There are 200 in the bag. We know that 60 are orange, so that means we must have 140 that are green. I'm doing a lot of things that I've been doing before in previous examples, but I'm asking the questions slightly differently. I'm realizing once you understand this type of math, if you're given enough information, you can answer the question regardless of whether you're going forwards or backwards through the problem, regardless of whether it's experimental probability or theoretical probability. So, is there another way of doing this? I'm going to go over here and just show that if I have 3 over 10 and I don't feel comfortable with this cross multiplication, one of the things I can do, and it doesn't look very different, and it is actually very closely related to what we're doing when we do this calculation, we can say I can expand 3 over 10 by some fraction, some version of 1, to get an equivalent fraction where the denominator is 200. I'm really doing the same thing. 10 times 20 is 200. So 3 times 20 will give me 60. And it's the same answer. So using fraction skills and avoiding the algebra skills, we're still able to answer this question. That's the end of the second page of my examples. Now we get to do one that I think is going to be quite a lot of fun. I'm going to take these pattern blocks out of here and put some different ones in using the same bag. This time, this is an experimental probability. I may as well erase and make some room so that we can write down some results. Okay, so what I have are white pattern blocks. They're just in this container, which used to hold margarine. And I have a bunch of them, and you can see them, but you can't see them very well. If you are able to see, okay, you might notice that there's some color in there. So we're back to that idea of random. With the previous experiment, when we had square ones and triangular ones in the same bag, it was a little trickier to make sure that things were random. But these ones, all of them are the same shape. They're all rhombuses. They're all white. They're all the same size and shape. So it's going to be easier to pull randomly. But the thing is, I want to have more than one type. I just don't want to be able to feel it with my fingers. So in this experimental probability experiment, some of them I have marked the inside with red with a Sharpie. And I should have done this before I put them all away. Others, here's one, have been marked inside with black. So therefore, we know that some of them are red, some of them are black on the inside, but we can't tell which is which when we're reaching into the bag. And I want to do an experimental probability. We're going to choose 10 of there are 20 altogether. I'll write that down. Where's my chalk? White rhombuses, and then we have some with black smudge. I'll call it a smudge because that's really what it was. Some have black smudge, some have red smudge. We don't know how many of each. don't use the word smudge very often. That's good to be able to use it. Okay, we're going to try choosing 10 with replacement. So we are not letting this become dependent probability. We're going to keep it independent by replacing them after we pull them. And what we're going to do is pull 10. I'm going to make a little table so we can put the results. I'll do it like this. I'll break this table into 10 cells. And we'll see what the results are from 10 polls with replacement. So this truly is experimental probability. I'm not expecting the ratio that we get to be exactly equal to the ratio of real black smudge versus red smudge, but it should come pretty close. So if we reach in the first time, I'll show what color I get, and then I'll mark it on the chalkboard wall. The first one is red. So I am replacing it. And I'll just put an R for red. Shaking it up, making sure that I don't make it more likely that I accidentally get the same one right in a row. I want it to be truly random. I do it again, and this time I got a red again. So we have 2 red. Let's keep doing this 10 times, and we'll see what ratio it suggests we have, how many red, how many black it suggests we would have in the bag altogether. This is, I got a third one that is red. At this point, I'm starting to think it's possible that there are more red than black, but I don't really know that for sure. Next one is red. Wow. Are they all red? We're going to find out eventually. Fifth one, red. I'm really starting to think there are probably more red ones than black ones, but I'm certain that I did not put 0 black ones. In fact, well, I showed you one of the black ones, right? Sixth one that is red. Do it again, shake it around. Seventh one is red. If they all turn out to be red, I don't know how good an illustration this is. But there's going to be a reason why that could happen. It's red. There are 20 of them altogether. What if 19 of them are red and only one of them is black? Then I wouldn't be too surprised with a result like this. Ninth one is also red. Red. We got 10 red. Well, this shows us that there are some limitations to experimental probability. This would suggest that will this fit? Yes, that all 20 of the ones I put in here are red and 0 are black. And we already know that's not going to turn out to be true. So let's count them. Well, you know what, I'm just going to tell the truth. I don't have to count them. I made them, so I know how many there are. And I'm going to tell you what the results, well, not what the ratio really is. Let me make sure that I don't get it wrong. I put 6 black and 14 red into the bag. Wow. So the chances of getting all 10 of them red, well, that's actually something that I would suggest might have been a bit unlikely. So there's that word unlikely again. But of course, this can happen. And this is one of the reasons that we really do usually prefer to use theoretical probability. But it's also a reason, sorry for the pause there, it's also a reason why when you do experimental probability, it's a good idea to have a good sized number of trials. So how many trials would it take for me to start getting results that come closer to the ratio of red to black that was really in the bag? Apparently, one trial of 10 pulls with replacement wasn't enough to get very close, at least not this time. So that's pretty interesting. It shows what experimental probability is and what it does. Okay, what is my next example? I'm checking the time as well. There's the time. We're about halfway through the hour that I was hoping to spend on this lesson. And that's pretty good because I'm halfway through my pages of examples, so I must be doing okay. So we're going to look at simulation next. Now, a simulation is where you would like to do an experimental probability to represent something that you know has probabilities associated with it. But the thing you really want to experiment with is not convenient to experiment with. So the example I came up with is the seasons. The seasons of the year, there are 4 seasons of the year. Depending on where you live in the world, that might be a little bit different, but the classic 4 seasons of the year, as I've learned them, are spring, autumn, winter, and summer. So there are 4. And the chances that a child is going to be born in my family, and no one is expecting a baby in my family right now that I know of, so the chances that the child that is going to be born into my family will be born in the spring, or the summer, or the autumn, or the winter. We can suggest that it should be roughly 25% chance of each, because there are 4 seasons and they're all about the same length. Let's say that there are 4 seasons that are 3 months long each. So the chances of a baby being born, if nothing else is affecting the probabilities, would be about 25% for each season. So how about we want to try to predict what season the next 20 babies that are born into my family will be born in? Well, we do not want to do a simulation that involves having babies, because it takes a long time for that to happen. We want to come up with a simulation where the probabilities are similar to the probabilities of the babies being born in the different seasons. And then we do the simulation with that other thing instead, that other thing being something that we can do our experimental probability more quickly. So what I'm going to use is the deck of cards. And this time, I'm going to use the suits. The suits, there are 4 suits. And there are equal amounts of each suit. There are 52 cards in the deck. There are 13 cards in each suit. The suits being the clubs, the diamonds, the hearts, and the spades. So I'm going to write some information down. I'm going to erase the experimental probability from the last example. And I'm going to start writing down some of the information from our simulation. Okay, so the 4 seasons, I'll write them in alphabetical order. Hopefully I can do that. So I'll write autumn, spring, summer, and winter. If these are each 3 months in length, which they are in some parts of the world, I guess, then we want to assign one of each of these to one of each of the 4 suits. So I can do that randomly as well. So let's say autumn is clubs. Spring is hearts. Summer is going to be diamonds. And winter is going to be spades. So our simulation is not going to be done by encouraging people in my family to have children. It's going to be done by pulling cards randomly from a deck of cards. I'm going to shuffle the cards. I'm holding them so I can't see the suits from the angle that I'm looking at them right now. And I'm going to do the simulation. We're talking about the next 20 babies. I'm going to do this 20 times, and I am going to be using replacement. I am going to put the card back after I pull it and write down the result, because I want to make sure this is independent. I do not want what card I get the second time to depend on what card I got the first time. So we have the independent probabilities. Let's see, let's just do this by putting little ticks. Again, I have to shuffle again because I accidentally saw one of the cards on the end. So I'll just mush it up a little bit there. And then I will pull a card, and it is a joker, which I forgot to remove from the deck. Okay, so let's get the joker out of there. And then open it again, and we have a diamond. This is the 4 of diamonds. I won't show it to the camera every single time. You're going to have to trust me. So the first one is a diamond. Shuffle a little bit again. Drop the card on the floor. pick it up before the dog can eat it. Oh, she's way over there. I think she might actually be asleep. Shuffle again because that happened, and what I have is a diamond. Okay, I'm going to try and make this faster, so I'm just going to shuffle very quickly and look at the card that's on the bottom. I got a diamond again. My experimental probabilities are really showing the limitations of experimental probability so far today. Fourth one is a diamond. Whew. Okay, so shuffle, shuffle, shuffle. I actually should have checked how well shuffled these cards were before I started, but I think they probably pretty much were. The next one is a club. Where's my club? Shuffle a little more. I got a second club. Shuffle a little more. I'm just trying not to look at the deck. And this one I have now. I got a diamond, the fifth diamond. I have to do this 20 times. I've done it 7 times so far. I got a heart. Doing it again. I got a club again. It's starting to look a little bit more, less diamond-centric, if you will. I'll do one more there, and I have a heart. So maybe this deck of cards doesn't have as many spades in it, but we know that's not going to be the case. It's going to have 13 spades and 13 of each of the suits. I got a 6th diamond, though. That's 6, 7, 8, 9, 11. I still need to do 9 more. 7th diamond. I finally got a spade. You can see why I don't want to do very many experimental probability examples. Not just because the results can end up being so weird, but also because it takes long. Here's a club, and I have to make sure not to accidentally do more than 20, so I'm going to have to keep track of how many I'm doing. Here's another spade. 4, 5, 6, 7, 8, 9, 10. We have 15. I need 5 more. Nearly finished, but it does take a long time to do a simulation. I got a heart. I got a diamond. I got another heart. 4, 8, 10, 18, only 2 more. I got a heart, so we have 5 hearts. And I got a spade, a 3rd spade. So we ended up with 4 clubs, 3 spades, 8 diamonds, and 5 hearts. Now we know that the probabilities are supposed to be roughly 25% each. Let's convert these into fractions first. 4 out of 20, 5 out of 20, 8 out of 20, and 3 out of 20. 3 out of 20 will not reduce. 4 out of 20 reduces to 1 over 5. 5 out of 20 reduces to 1 out of 4. And 8 out of 20 reduces to 2 out of 5. If we convert it to percentage, this is 20% clubs, 25%, what was that, hearts, 40% diamonds, and 15% spades. Actually, the results seemed a little weird at first, but they sort of normaled out a little bit, and they're not really that bad considering that I only did 20 pulls. It's the number of trials. If I were to do this over and over again, several trials, and get much bigger numbers, what would happen is the experimental probabilities results, these percentages, would get closer and closer to the theoretical results, where all of them should have been 25%. So what happened with the hearts that I just by luck happened to get exactly the same percentage that I would have expected from theoretical probability. For the others, not as close, especially those diamonds, really not very close. That's experimental probability for you, but that's also an example of a simulation, which is why I wanted to do it. Okay, I'm done with the cards, I think, for this lesson. And I'm done with this page, so I'm going to move on to the next example, which is a sample space, an example of sample space. Now, I'm sort of jumping around in the topics a little bit. I'm not necessarily doing them exactly in the order that I did them in the first 3 probability lessons, but for my sample space, I'm going to talk about a scenario, a situation that we all deal with sometimes, which is when we choose our clothing. How many people choose their clothing randomly? Not many. People choose their clothing for reasons. I wear soccer jerseys and rugby jerseys to work every day. I choose them for various reasons. Sometimes I know that one of the big teams has been in a big game recently, and if I'm happy with the result, I'll wear their shirt. So you'll see that I might be more likely to be wearing, say, a Real Madrid shirt after the Champions League final, because they seem to play in it about 2 out of every 3 years. I also choose my shirts because they're sports team jerseys. I also choose them partly because of which teams I like. So, for instance, I have at least 5 Barcelona shirts because I like Barcelona a lot. I only have one of those Real Madrid shirts because I'm not really that fond of Real Madrid. And I have a lot of Liverpool shirts as well. So you would have seen those more often if you have appeared in my classroom a lot. So what I'm going to talk about for my sample space example, though, is to start with just the trousers and the color of them, and the shirts, and it'll just be the color. So I have 3 shirts that I'm using, and this one, although you can see there is a little bit of orange trim in it, I'm going to refer to this as the white shirt. It is a white shirt. It happens to be the Netherlands national team jersey. And then, speak of the team I don't like very much, my red shirt happens to be Real Madrid shirt. And I have a yellow shirt, which happens to be Bolton Wanderers, and it's kind of a mustard yellow. It's not the nicest yellow I've ever seen, but that can be part of the reason that I buy it. Again, this idea of how we choose colors of clothes, I don't have very many yellow jerseys, so when I get a chance to buy one, I'm going to buy it because it gives me more choices when I'm coordinating the colors of my clothing or whatever it is I do. For my trousers, the colors that I have chosen for today, they're all jeans because I wear jeans a lot. These are brown. It's kind of a light colored brown, but I'll call it brown. These ones are blue and these ones are black. So we're going to make an example, and I'm going to draw it on the chalkboard wall of a sample space. Sample space shows you all of the possible combinations that can happen. So I'll erase this. How do we show all of the possible combinations that can happen of these 3 colors of shirt and these 3 colors of trousers? Now, I'm not wearing 2 shirts at once, and I'm not wearing 2 pairs of trousers at once. So once I choose the color of the pair of trousers and then choose the color of the shirt that I'm going to wear with it, at that point I have made my outfit for the day. We're not including socks and shoes and things like that right yet. So, let me see my little drawing. I'm going to... There's more than one way of doing sample space. So the tree diagram is what I'm getting at, and that's probably my favorite, and I think it should be a favorite with students as well because it's very visual. You can really see what you're doing with the tree diagram. But I'm going to start by showing another way of showing it, which is just to use abbreviations and group together, maybe, let's say, with brackets. So how about, made a mistake because I chose, this is so annoying that happens with probability. I chose blue trousers and black trousers. So I can't just use a B. So no biggie, I can fix that. I'm just going to say BLU is my blue trousers. It's enough of the word to write, the 3 letters. And I can combine that with the red shirt. And then I can put a comma, and then I can do it again, except I want to choose something else. I want to show all the different things that can happen. So I can write BLU, which is the blue trousers again, with the white shirt, and then BLU, same trousers, with the yellow shirt. I'm not finished, but what I've done is I've shown all the combinations that involve the blue trousers. I can put black trousers with the red shirt, black trousers with the white shirt, black trousers with the yellow shirt. It does take a bit of time to do this, but it's going pretty fast. And then finally, the last color was the brown. It also starts with B. Why did I choose 3 colors of trousers that all start with B? So I'll put BR for brown, at least it's a little shorter. Brown trousers with red shirt, brown trousers with white shirt, brown trousers with yellow shirt. Now, not all of these color combinations are going to look as good as each other, but we're talking about what are all the combinations that are possible. So if we were to choose randomly, if I chose the trousers in the dark with my eyes closed, and I could those are the only three choices that are available. I'm not going to be able to choose the color. I'm going to randomly get one of those three colors. And then I go up to the pile of three shirts and the same thing happens. I'm going to choose them randomly. Well, these are all of the things that can happen. And we can see that there are actually 9 things that can happen. 9 possibilities. It is quite a lot of possibilities. Only 3 shirts, only 3 pairs of trousers, and yet 9 different outfits, if you will. So that's interesting. And what is another way of doing that? We can say 3 shirts, I'll put 3SH, times 3 trousers, 3TR, 3 times 3 is 9. Oh, so there you see a little bit of a shortcut. And when people become familiar with probability and comfortable with it, then we end up using a lot of shortcuts. But in order to visualize what we have, the sample space is useful. Now this is a form of sample space, but I want to do it again using the tree diagram, which means I have to do some erasing and make some room. Look at the time. We're done quite well with time. I knew this sample space one would take quite a bit of time because it involves quite a lot of drawing. And I'm not trying to draw really beautifully or anything, but I need to express it. Now, let's do a tree for the blue trousers. So again, I'm using BLU. That looks too much like a BLA, so I'm going to switch to using block letters. BLU, that's my trousers, and then there are 3 things that can happen with the shirts, which are the red shirt, the white shirt, and the yellow shirt. But blue trousers wasn't the only choice, so I can also show my BLA for black trousers and do this. Now the only downside to these tree diagrams is they could get messy. When you have a lot of possibilities, if you were to make a much bigger tree diagram where you're showing trousers and shirts and shoes and socks, it could get hard to get it to all fit onto the same piece of paper. The black trousers go with the same choices of shirts, so I'm repeating this. Red, white, yellow. And then there was the brown trousers. I'll just put BR, and I'll leave enough room for my 3 choices, red, white, yellow. Now another thing we can do is we can express the probability of getting each item in the form of a fraction. So the blue trousers, if it's chosen at random, there's a 1 out of 3 probability. 1 is successful, 3 is total. Well, the black trousers are also 1 out of 3, and the brown trousers are 1 out of 3. Then we have the shirts. Well, there are also 3 shirts. So it's not always going to be 1 out of 3. Sometimes you're doing something like this with 4 different colors of shirt or 5 different colors of shirt. But we have a 1 out of 3 chance for each of these. And this becomes highly repetitive. But I always tell students it's worth the time to do it. Now, what else can I see from this sample space? I can see the number of possibilities, all the possible combinations, like I could with the other form of sample space that I showed. I can just count the ends of all these branches and realize, well, there have to be 9 possibilities. And we already knew that was going to be the result. I'll write 9 combinations. We can also use the tree diagram and the fractions to calculate the probability of something happening. So what is the probability of getting, say, brown trouser with white shirt? Well, the brown trouser was a 1 in 3 probability. We showed that here. And the white shirt is also a 1 in 3 probability, and we're going to get it. This is a 2-event probability problem. It is independent because what color shirt you get does not depend on what color trousers you got. Not the way we're doing this situation. And therefore, we're going to get the probability of getting the combination of brown trousers, white shirt by multiplying the 2 fractions, and we get 1 out of 9. We can convert this into a percentage if we want. I believe it's going to be 11.1% with a little bit of rounding. Did that fit on the chalkboard wall? Everything's fitting on the chalkboard wall. I could almost walk outside and it would still fit on the wall. That seems impossible. There's that word impossible again. So that's very useful. The sample space allows us to see so many things. It allows us to see all the combinations. It makes it easy for us to make sure that we get our fractions right. It allows us to count the combinations, and it allows us to answer all sorts of questions. And one of the things I like to do with the tree diagram is to circle the pathway through the tree that goes with the answer to my question. So this brown trousers with white shirt is this pathway right here. And it's easy to have confidence in my answer because I do it this way. Let me check the time. We're getting down into the last 10 minutes of our lesson. I don't want to do a lot of sample space problems because it took so long to draw all of this. But one of the things I'll do, just as a little tease as how could this look different, is let's modify this a little bit by also including a choice between two pairs of shoes. And these, I'll call these the tan shoes so that I can avoid the brown abbreviation. But I'm going to have to call these black shoes because they really are black. Although, if you got a close look at them, you would see that there actually is quite a lot of chalk dust on these, and that kind of reflects what I spend an awful lot of my time doing. Because whether I'm at home or at the school, chalk dust is landing on my shoes. Okay, so we're not going to actually use the shoes. They are just a prop. I'm going to put them aside. But how can we modify this if we're also considering all of the combinations of all of these outfits with the black shoes and with the tan shoes? Where can I do this? Okay, there's two ways that I can modify it, and I don't really have the space to do this one. I could put black shoes here and branches going to all of these, but then I'd have to draw another tree diagram just as big with all the same stuff and brown shoes. Another way of doing it is to split the combination, the one at the top, which is the blue trousers and the red shirt. We could have the black shoes or the tan shoes. What's this going to do to our end result? Now, like I say, this can be very repetitive. I would have to do this again here and here and here and here. I would have to do it 8 more times. So we start to realize that once you get into a really complicated situation, you don't necessarily want to have to draw the tree diagram sample space because it would get to be so long to do. But then the underlying math will still work. So I'm going to ask the challenger question and then see if I can answer it. How many combinations will there be now that we've included all of those shoes? Well, how many combinations? Remember we calculated the number of combinations earlier by saying there were 3 combinations of trouser, and we multiplied it by the 3 combinations of shirt combinations. The 3 choices of trouser multiplied by the 3 choices of shirt, and we had 9 combinations. So that was right before, but now that we're adding in the shoes, there are 2 choices of shoes, so we have to multiply by that as well. 3 times 3 times 2 is 18. So it's not the only way of answering the question. If I had made the diagram much bigger, I would have eventually seen that there were 18 endings to these pathways through the branches. It would have taken a long time. Well, this certainly didn't take a long time, and it's giving me the same answer. That's useful. When you experiment with some of the smaller situations where you can really draw it out and see it, you end up seeing how the patterns work, seeing how the underlying math works. And then you're able to rely on the underlying math when you have to, when you're given a situation where it's not convenient to draw the sample space out in all this detail. I like that. Okay, so I have covered everything from the unit of probability except the stuff that we were spending all of last week on, which is the dependent versus independent. So I only left myself, how many minutes? Theoretically, I only have 6 minutes left before I've used up an hour. I'll go over if I have to. But I'm not going to do too many examples of dependent and independent because I did spend a whole hour on that and I videotaped it. So I'm going to have to erase here. It seems such a shame to erase something after you've worked so hard to draw it. But that is the magic of video, isn't it? And the magic of having cameras of all sorts is you can make a video and then you're still able to see it after you erase it. My students in my classroom use their phones to take photos of the things that I demonstrate on my chalkboard, and it's probably the best tool I've ever seen students using in school, because when I was young, we didn't have cell phones and we didn't carry cameras around with us all the time, so we couldn't do that, and you ended up having to copy things down and you lose your chance if something got erased too soon. My students just take a picture whenever they think it's something useful and they want to be able to look at it again. They take a picture. It takes them 1 second. I just get out of the way and they snap the picture, and then I erase and I do my next example. Really fun for the teaching. Okay, so I want to do a dependent and an independent example. I'll start with simple ones, but I want to use some of my new props. So I'm going to use something. Where are my bags of stuff? Right now, this has the white rhombuses that have either the black smudge or the red smudge. They're in there already, so I may as well use it. And I'm just going to do an example of dependent and an example of independent. Why are these words always so long? Independent over here. And I'm just going to do the example side by side. So I'm going to answer the same question, but I'm going to answer it dependent-wise and answer it independent-wise. So the chances of getting a red smudge followed by, and it's dependent, so that means that I want to keep it. I'm not putting it back. Red smudge followed by black smudge. How about that? Now we did calculate, we did find out how many of each there were. I'm going to have to refresh my memory. 14 red, 6 black, I believe. Yep, 6 black, 14 red. So the chances of getting a red are 14 out of 20. There were 20 of the white rhombuses in here, remember? And we're multiplying it by, because we kept that one, we now have only 19 rhombuses, and the chances of them being black, well, I took a red, so all the black ones are still there, so that's 6 out of 19. We have some rather large numerators and denominators. We can do a little bit of canceling, but I won't bother. I'm just going to multiply and use the calculator if I have to. Okay, 6 times 14, 6 times 10 is 60, 6 times 4 is 24, 60 plus 24. 84 is my numerator. 20 times 19, 10 times 19 is 190, so 20 times 19 will be 380. Okay, do I want to try and convert this into a percentage in my head? No. I will let the students do that if they want. I'm just going to do it with the calculator. 84 divided by 380, 22.1%. Now I'm answering the same question, but I'm keeping it independent, so that means I'm putting it back. So the chances of getting the red are going to be the same as they were over here, 14 out of 20. But the chances of getting a black are not going to be 6 out of 19, they're going to be 6 out of 20. There still are 6 black ones, but because I put that red one back, there are 20 pattern blocks, white rhombus-shaped pattern blocks in the bag. Now I could do a bit more canceling here. It would cancel a little easier because I have an even number in that position, but I'm still going to do it with without canceling or reducing the fractions, and then I'll use the calculator as I have to. 6 times 14 is still 84, and 20 times 20 happens to be 400. So 84, all that I might be able to do in my head. 84 over 400, if I reduce by 4 over 4, gives me 21 over 100, so that very quickly gives me 21%. Not very different, but it is different. So if you keep and it's dependent, the chances of getting red followed by black are slightly larger than if you put back and make it independent. 22.1% is larger than 21%. So there's only one more example I want to do, and I want to do it this way. Again, I want to do a dependent and then look at the same question but done with independent, but I also want to do one other thing. Where is my microfiber cloth? I'm going to, instead of only doing 2 events, I want to do 3 events. I haven't done very much of that. And the truth is, you can do this with multiple events. You can do it with 3 events, 4 events. You can do it with as many events as you want. Mostly for our unit, we're keeping it down to 2 events because it is a beginner probability unit. So, and I want to also change, I think I'm going to change which bag of tricks I use. Which bag of items I use. So I'm going to get that same bag, but I'm going to shake out all of the white rhombuses with the red and black smudges. And I'm going to put into it instead the red, blue, and yellow hexagon trapezoid. Oh, okay, pick that up. There we go. The hexagons, trapezoids, and rhombuses. These blue ones are also rhombuses. They're just rhombuses with the angles a little different than the white rhombuses I used before. So to remind you, and I am just hitting an hour, so I want to finish this up, and this will be the end of the lesson. To remind you, there were 12 altogether. The total is 12. There were 3 yellow, there were 5 blue, and there were 4 red. We're not actually pulling them out of the bag. This is theoretical probability. The question I want to ask, both dependent and independent, is going to be, and remember, pulling randomly, meaning we're not trying to feel to see if something's a hexagon or a rhombus, or was the other one a trapezoid? No, pulling randomly means we are making ourselves do it randomly. What are the chances of getting yellow? And because this side is dependent, I am going to keep, followed by a blue, I'm going to keep, followed by another blue. So I'm answering the question both times. Yellow, put back, I'll write PB for put back, blue, put back, and another blue. Okay, so we're just doing the same thing, except it's 3 fractions that we're multiplying instead of 2. So the chances of yellow, there are 3 yellow out of 12. I can write 3 over 12, or I can reduce it to 1 over 4. Then the chances of blue, because I am keeping them, this goes down to 11. The total goes down to 11, but all 5 of the blue are still in there. And then for the third one, I'm keeping again, so the denominator goes down to 10. And now there are only 4 blue because I took one and I kept it. So I have 3 times 5, which is 15 times 4, which is 60. The numbers get large very rapidly when you do this. None of these numbers were very large, but the answer is pretty big. And then we have 12 times 11, which is 132, times 10, which is 1320. I'm going to use the calculator. Where is my calculator? I convert it into a percentage. 60 divided by 1320 gives me 4.5%. Now we're going to answer the same question, but doing it independent with the put back. So we still start with 3 out of 12 for our yellow. We're multiplying that by 5 out of 12 for our blue. Yes, there are still 5 blues to choose from, but there are now still 12 we put back, so there are 12 in total. And now it's still 12 on the third one, but now now, yes, I put back, so it's going to be 5 up here again. So the answer is a little different. I might need the calculator a little bit more. 5 times 5 is 25 times 3, that's 75. And then 12 times 12 times 12, otherwise known as 12 cubed, 1,728. We look at that, and it's hard for me to judge whether it's a better probability or not just by comparing the fractions, which is why the percentages are so useful. So I'm going to convert that to a percentage. 75 divided by 1,728 times 100 gives me 4.34%. If I want to round to the nearest tenth again, I'll call that 4.3%. So it turns out the probability of this happening is lower if you're doing it independent with the put back than it is if you're doing it dependent with the keep. But it's not a very big difference. That is it for my review of the unit of probability. It has been a lot of fun covering this topic. The next topic I want to get into is statistics. And there's an overlap between probability and statistics. So some of the concepts that we use for this stuff we will use when we do the next unit, which will be statistics. I'm looking forward to that. I want to say goodbye. Mocha, come here. I want my beautiful assistant to get a chance to say goodbye. Oh, she's really relaxed. Hope she wasn't too bored listening to all of that probability talk. So I will see you next week, and thank you very much.